Yes. So we will be talking about feed-forward error-correcting neural networks, which is a different approach to the network type we considered yesterday, which was competitive learning. So where neurons basically compete on each and every neuron compete for attracting a certain pattern in the input signal or input vector. Here it is not like this. So here in this type of learning, we actually learn parts of the representations of the input patterns, which lead to certain classification, a desired classification outcome. And this type of learning, so for this type of learning, we need to assess correctness. And this is done with the help of the cost function. So at the very, very last stage, we want to compare the results. And that what is happening here in line, let me see what line. In cell 5. Yeah, in cell 5. I don't know what line it is. And it is very simple, formula. So where y hat here is the scores produced by the network for a given input, and labels. So this is the ground truth. So the desired outcome. And what is happening, and this D is an array that collects the gradients. We'll come to this soon. So what is happening in this row is a little bit, or it can be interpreted wrongly, and most of people interpret it wrongly. So because they say this is the cost evaluation of the cost function, or this is the cost function. And so starting from this point, I will show what it is in reality. Or maybe you can tell me based on your current knowledge. So I'm saying this line corresponds to the evaluation of the cost function. But what is the cost function here, which is evaluated? How do you know?
So remember something minus, you take the difference for the correctly classified in the log.
But here we don't see any log.
This is the derivative.
Yes. So how many of us are on the same page? We will. But thanks.
That was right.
Yeah, that's right. So let's go then.
May I ask you something?
Yes.
The dot D, is that like the derivative?
Yes. So you compute the derivatives and use it in the backwards path.
But is it the gradient or is it the derivative?
Later on, well, it is a gradient. Yes. Yeah. It is. So let's start. So we talk about feed forward. Error. learning or neural networks. So we talk about these networks in the context of solving classification task. Using supervised learning approach. And here we learn representation. So the ground idea is that we have input. So it's our vector of features. So x1, x, n. So this is our feature vector. And the overall idea is very simple. So we model a category, so a class, as a weighted sum of features. Now I will again draw this famous. So and here we do computations and produce a score for a certain class. And again, so in the machine learning context, artificial neural networks, this thing is not is usually called neuron. So and but essentially, so for us, it's important that we consider this as a computational element. So here we compute certain function. So for now, so let's not specify exactly what this function is, but so it's a function. So we call it f act. So it's activation function. Again, these words, or specifically the term activation. So this reflects this biological inspiration, and that this thing is a mathematical model of a neuron, so that it is activated by certain input, and so when there is a kind of threshold that the input should surpass, so that the neuron performs certain activities. But in our case, again, so we are talking focusing on the algorithm. So and so we for now we denote it as activation function. So again, mathematically, we have we can say that, okay, so we have our y hat. So this is again our class score equals, in the very simplest case, act of sum of y1 to n v I x I. And the idea of learning, or the whole optimization procedure is to improve the score for each class, so that it comes closer to the desired outcome, to something what we call as ground truth. And here again, so we very quickly come to a question. So how can we first observe the dynamics of the score, and how can we what can we adjust to improve the score? So these are the two questions. So the core training principles of error correcting neural networks are or a recipe. So yes, sorry, no. Recipe. Recipe. I always have to. I need online access to ChatGPT. I think this is the correct spelling of error correcting. Error correcting artificial neural network. So it includes two items. So first, we need a loss function, or error function, or a cost function. So synonymously. So these terms are used interchangeably in different contexts. So a loss function or cost or error. So we need to assess the current outcome of our model to the desired outcome. And moreover, so it's not any function whatsoever, but it should be differentiable. And why do we need it differentiable? Why bother? Why do we need to compute gradients or
Gradient descent. Because we want to minimize something. We want to find a minimize loss.
exactly? That's
I think that's response to
yeah.
think of like
So
minimize.
yeah, so again, so we will not go back to the basics, but I mean the only thing to what is relevant here is that the derivatives, they are measures of sensitivity of a function to change in particular variable. So it's a measure. So, So now we talk about any function. A variable. Right? And that's why, so I mean, the whole training is about, so if we go back, uh, I mean, the variables here are these weights that is what we can vary. And we need to assess the influence of this variable to the behavior of the function that assesses the quality of this outcome. So essentially, so this loss function normally is denoted as as J. I mean, it can be denoted in lots of different ways. And I mean, in general form, it takes two parameters: the output scores and the desired outcome. Now, of course, we can discuss how to encode this value. So normally, I mean, we talk about some symbolic categories, but they need to be converted into numerical format so that they become comparable, mathematically comparable with the output scores of the network. But what we are doing here is essentially the whole learning is about taking this taking partial derivatives of this cost function, and now so I put this f act x and dot. So that is in vector notation now, and the ground truth. And we take this derivative. So we try to understand which of the features actually contribute to the change of the cost function. So we take it with respect to each and every weight variable. So and this is our gradient. So the actual learning rule is now rather simple. So we want to adjust the weights according to this to the outcome of the optimization. So taking into account this derivative. So learning rule. So we want to compute. So this is that you want to compute new weights, which is the current weight minus d dB. So minus, here, I mean, basically, this is also a comment to what to your question. So do we compute derivatives of gradients? I mean, derivatives are our gradients. I mean, and so we this learning rule, this minus signifies that we want to implement an opposite trend to whatever gradient. So we want to adjust our weights in the opposite direction. And then also you normally you scale the effect of change. So you want to avoid very drastic changes of the network, because in this case, I mean, when you have many variables, I mean, with very drastic changes, you may, or you will end up in a situation that you won't converge to the desired optimum solution. Yeah, so this would be our learning rate. And this function you will see, so I want you to identify as part of Lab 5. So you will see in part of the code, so exactly this implementation. But let us now generalize this model. So let us have a look to our starting point. Our starting point is a very simple model. So this activation function in the simplest case can be just summation. In this case, we have a linear model, obviously, and which we have learned previously in different other contexts, that doesn't allow to effectively separate the categories when they exhibit nonlinear behavior. But not only that, so sometimes we talked about this phenomenon in the context of the kernel trick. So sometimes you want to include high-level interaction between features to increase to improve the separability. And that is kind of a very shortcut way explaining the shape of the artificial neural networks. So this multi-layer, what is called multi-layer perceptron. So which is basically so MLP. It's a generalization of a model, so which includes high-level interaction between features. What do I mean by this? So normally you kind of a layered structure. And which essentially reflects this high-level interaction between initial features. So if you have this x1 through xn, you print this kind of structure. And they have photo also. You have the same kind of connections for them. But at the end, so it all converges to it's sort of all same goal of act of computing a class score. And you have several of such classes. So now we come to, at least from my understanding, or the way how I kind of arrived to my current understanding, this structure over here is hard to comprehend mathematically in this way. So it's easy to draw graphically, but so there is no kind of immediate shortcut mathematically. So what I prefer to do is to trace just one of the a portion of a network. So say just I isolate isolate one of the pathways of the pipeline. And in this case, so the structure becomes like this. So you have your feature, and actually, so when isolating, even here I managed to. So we can even isolate it with respect to a single input, like this. So what we have? So we have our x I. So the row data. Then and this is input. Normally, you can augment it with kind of dummy computational unit that just pass it through with certain weight 1. Then it goes through f activation, where then again, so it that is given another weight, v2, then f act. So again, weighted, and pass it to final activation function, and further to and this is the output. Yes. And here there is an obvious observation, so we can differentiate the input layer, the output layer, so and the computations in the middle, which are normally referred as hidden um, computations with respect to input and output, which are kind of directly observable. So here we have one hidden layer, and here we have another hidden layer. But again, what is it? What is in it for us? So that's still a kind of algorithmic view on it. So here we can write it like this. So our output is actually f act of W3 multiplied by f act of W2 multiplied by f act of W1 multiplied by our input. So this is what we have essentially. And now, so we will see that these activation functions, so they should also possess property of non-linearity. So and kind of there are different explanations for why would we like to have it non-linear activation, but one of the explanation is this is the means to achieve generalization. So that when you to introduce uncertainty, basically, so that your unknown examples so the classification to a given category goes along a kind of smoother trajectory, so to say. And here we have different options to implement these activation functions. What are these options? Now, you who are experts in machine learning, you should tell me. For f act. Yes, but I mean, in principle, again, here we can use any differentiable function. So it needs to be differentiable. Why? Because so later on we will introduce this more formally closed function, so which allows us to monitor the quality of the output. And when we take the derivative, so we will take a derivative with respect to all these w's. And as such, all of these functions, which include this variable, so they should be differentiable. But there is another kind of explanation, or maybe post factum explanation. I don't know whether it was kind of done this way, but you will see now what it is. So you said sigmoid, right? Sigmoid. So good to see to have it visually. So you have 0 here. This is your sigmoid of x, and this is x, and this is 1. And so it looks like this. It is defined more formally like this: a 1 over a 1 plus exponent minus x. Again, what is special about this function, except for this smoothness of transition for a given range of values of x? So you see that it, I mean, it has some limits, obviously, and some smooth transition. So that's the desired behavior for achieving separability. But the interesting observation you could find if you take a derivative of this. So here is not a partial, but I mean this usual derivative. So d sigma x by dx, which is actually like this: the sigmoid x 1 minus sigmoid x. And this is actually smart because I mean, if you think about it, so this derivatives you use as part of the optimization process on the backwards path, but you compute it based on the actual values of variables when you pass it through the network. Basically, the derivative is computed at the same time when you compute the activation function. So that's kind of so. By the way, your forward path is ended, all derivatives are already computed. So and it's just to kind of the whole flow, algorithmic flow of the backwards path is just to kind of take this array of computed derivatives and accurately compute the gradient, the new weights as specified by this equation. And the same thing again. So there are different couple of other alternatives. So second is hyperbolic tangents. It is like this. So it has different range, -1, 1. So it looks like this. And it has the same property that you compute the derivative at the same time when you compute the activation function. So basically, tan h of x is e of x minus e minus x divided on the sum of these guys minus x. And d tan h dx is 1 minus tan h square of x. and obviously ReLU. So ReLU is a very simple function. So it's a linear function. So it preserves all the positive values and it cuts all the negative values. So it has zeros, well, until until a region, and then it goes like this: x re low. Yes. So it is computed as 0. Oh, sorry. So it's a max of 0 and x. And d real dx is 0 and 1. So 0 for 0 and 1 for x. Connected to this different functions. So as I said, so their purpose is to assist in the optimization process. So that is to avoid kind of drastic changes and being limited within certain range. So the explanation is rather mathematical. Connected to this, and I think I have this link in the connected to the first module. So let me double check it. Performance metrics. Maybe it's here. Yes. Have a look at this training, this PDF. So it's well, rather old presentation from Hinton about pre-processing and stuff. So actually, looking at the shape of the functions, activation functions, I mean, this you can already make a certain opinion about the desired range of input values. So, for example, if you have only, say, positive values in your input, so then this ReLU will simply not work, right? So, I mean, the idea with ReLU, so that I mean that subsequently, so you cut the negative values, but if there are no values, so nothing actually happens with respect to nonlinearity. The same as here, so your input values should span to the negative part, so being centered around 0. So that's also one of the reasons we do pre-processing, because of the requirements of the downstream functions in machine learning algorithms. Right, but then so now we come closer to to the definition of the cost function itself. But before that, so let's talk a little bit about the output. So so far we talked about neural networks as a function, this complex function producing the scores. So numbers corresponding to different classes, and then you take basically the minimum of it. So, but again, to be treated mathematically, so you can have you need to do an extra computational step. So what you can do, and that what is happening here. So 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 you want to normalize your output, so so that you can compare it with your output encodings. And so as an example, so here there are different variations. So you can, again, so you can live with, you can have different options on what to do with the output and how to specify the error function. What we will look at is the approach that converts scores into probability distribution. Um, and the reason is well simple, because I mean in the probability domains we have a well-defined measure of similarity between the distributions, and that way we can this measure we can use as our cost function, so we can see how the outcome. So we can judge on the quality of the outcome from the, different outputs collectively. So as a distribution. So on the one hand, we will have the desired distribution where we have with 100% certainty, we know that so this particular example belongs to category 1. So, and this can be achieved with, say, with something which is called one-hot encoding. So, and it means that say only so you in the one-hot encoding you have number of positions corresponding to number of categories, and only a single one becomes one. And you can treat this one-hot encoding as target probability distribution across all possible categories, and the outcome of the neural network as the resulting probability distribution, and you want to compare these two. So, and that will become your cost function. But first thing first, so we want to convert the scores into probabilities, and this is done by normalization using so-called softmax function. So softmax activation. So what it does, so it takes scores. This one as C. So this is the scores for classes 1C. So this computed at the so that you observe at the output. So you pass it through this box, and you get the normalized version. So we denote them as P1, PC. And the thing is that this normalization is such that sum of Pi I equals 1 to C equals to 1. So that's what you do. That's what allows you to treat this output as probabilities, because they sum up to 1. And this softmax then, let's denote it as S, is defined as following. So for the score S J. So for one of these scores, it is equal to e to the power S J divided by sum of e to the power S I equals 1 to number of classes. I found it actually. I'm using to do the calculation myself. I mean to do the derivative because at the end you kind of arrive to a very satisfying result. So I skip a couple of steps and just write the final thing. So we need to be able to compute the derivative of this stuff with respect to the inputs. So we want to modify these inputs so that we see the changes in the function. So the derivative ds of Sj. So with respect to this to actual to S. So okay, so it depends on the which one of this. Since all the scores are involved in the computations of the output of softmax, so we are talking about derivative of this function with respect to any of the inputs. So and that's why it has two cases. So for k equals j, and for k not equal j. And in this case, it is so S j. So basically the output 1 minus Sj. So again, despite the fact that I mean we have this exponentiation in the forward computation, the derivative is computed based on previously computed number. And so for the other case, it is J multiplied by Sk. Yes. But again, if you want, you can trace this computations yourself. What is important, I just want to complete the figure by introducing this the cost function, the error function. So the function which we'll use to assess the outcome. So we want to assess the quality of the outcome with respect to the ground truth. And using this specific setting, so that we actually do normalize the scores, normalization with this, so that the output consensus properties. So we can treat this, as I said, as a probability distribution. So this here at the output we will have real values. Most of them will be smaller than well the desired output or one of the categories, and we want to compare it to the real outcome. And for this, we use something which is called cross entropy. Which is nothing more. I mean, in simple words, it's a measure of similarity between two probability distributions. So in our case, so we will differentiate two of them. So now again, I will rename a little bit these notations because these notations are normally used in the context of probabilities. So we on the one hand, we have our piece, so the outcome of our neural network, and on the other hand, we have a probability of predicted labels. So in terms of notations in the lab, so this what will be computed as y hat, and this is the vector of outputs. So let's say y hat is a probability distribution of predicted predicted category or class, and y is a probability probability of true class. Right? CI. So we have and we denote it as PI in the previous notations. So PI and CI is the probability of the true class. So and if we treat them as probabilities, then we can define also complementary probabilities. Which is 1 minus CI and 1 minus PI. So this is basically correspond to wrong classifications. So what is cross entropy? So how is it defined? So cross entropy. So we have H. So you have probability for correct class and probability for of predictions. And actually, so this equation over here tells that it's minus CI logarithm PI plus. So I will so 1 minus CI logarithm 1 minus or actually sorry the actual formulation is we have a minus here. A 1 minus PI. But it can also be rewritten as minus some CI ln PI plus 1 minus CI ln 1 minus PI. So this is our measure. So I mean, when computing this stuff, it tells us how well our outcome PI corresponds to the desired outcome, which is CI. And now I should stop. And so next time I will complete the figure with the last bit of information. Yes.
Upload this to.
Absolutely, that will be online. But the thing is that so starting from here, So this is the function that actually is optimized, because it is here where under this PI is hidden all the computations within the neural network. And you optimize this function by taking a derivative, but by all the variables which are in-baked in this PI, in the computation of this PIs. So all the weights, etc. And so I will, next time I will just show you the kind of the beginning, the sketch of the beginning of computation and the final outcome, so that you can match to the implementation and the code. Okay, that's it.
Thank you.